Moving on to the next one, it's going to be Professor Satoshi Matsuoka. He will discuss the intersection of HPC, AI, and quantum technology in Japan. Please welcome him to the stage.
Okay, thanks for the invitation. I have to go real fast, apparently. Okay, so what we're, first with AI, so what we're really thinking is trying to go from the 20th century way of doing science, where we have small labs, human experiments, transfer knowledge through papers and all that, to this industrial revolution of science. Right? We want to automate the process. We have principal AI scientist agent working in tandem with humans. And then then we have very domain-specific various sub-agents and various tools. And then we have a data acquisition, humongous data acquisition infrastructures, and we drive this autonomous science discovery loop. And then the agents will talk with each other to do the science. I mean, this is exactly how we see our productivity increase by multiple factors in the coming years. Now, with AI for science, a lot of people confuse just AI for science just hosting LLMs, but of course that's not true. In fact, back in AI for science, there are multitudes of different divergent type of models. For example, in order to support big simulation, you have a variety of surrogates of various domains or physical informed neural networks. To handle very large data, you will probably have to have some sort of generative AI of being able to handle very large image data sets, images that go from like terabyte per image, coming out from our light sources, and also maybe a humongous graph neural networks and stuff like that, which are non-lingual. That's the important thing, because when people talk about AI in the normal space, they'll only think about LLMs. But in science, you have varieties of all these different types of models which are not lingual, right? And we have to support. And these are very expensive to support. And then we have the AI sciences, which are, of course, driven typically by LLMs, and of course have agentic systems. And to be able to support all of these AI models, the divergent AI models in our infrastructure is very important, and that's how I would design the system. Now, the Japanese government is now starting to really aggressively fund these efforts. So they put together about $1 billion package. Some are like old money, like how try to design Fugaku NEXT, of course, which will, of course, be an AI for science, heavily AI for science machine. But also they have some new money, about $250 million going into domain science program for supporting AI for science, new AI for science initiatives. Right? So, and this is just round one, by the way. So it's, because they got like tons of applications. So it could very be likely that they'll have round two next year, even with more increased funding, hundreds of millions of dollars. But it's very important not to spend money on infrastructure, but also to spend money on domain science. But of course, it's important to spend money on infrastructure, right? Otherwise, if you support domain science, then where are you going to compute, or you run the AI? So at Riken, we're putting together this modest-sized cluster. It's not huge. It only had like 2,000 Grace Blackwells. And this is just coming into production. We're in pre-production now. We're going to almost production phase. But these actually consist of 2 GB 200 MBO4 clusters. ICACs are very, very fast, very easy to use. But the important thing is to really figure out how to operate this machine. And some of these were already mentioned by my colleagues, but really to design AI for science supercomputer, which consists of software stack that are based on the tried and true Fugaku NEXT. In fact, Fugaku's software stack. In fact, this is a already worked on virtual Fugaku to abstract out this really hardened HPC software stack, and then and includes a lot of components, open source components as well. Well, a lot of tool chains, a lot of components from DOE, also for ECP, a lot of stuff we developed. And then we're adding lots of software stack from for AI, for large data handling, Also lots of models, open agentic harnesses and so forth to construct a software stack. And then defining a service layer so that it's not just about batch queue. We have we'll be supporting very secure agentic services because they have to be secure. So we developed this environment called Revault, which is basically a sandbox environment for running agents, because we can't just let agents run run amok and destroy all your file system or leak data. So this is also being developed so to be a package that can be run on any system. So if you're interested, you can contact me. And all these is culminating into big international collaboration, in particular with US DOE. So the DOE has a Genesis program, a Genesis mission, and now we've been working on establishing strong collaboration. And in the beginning of June, it was announced that Japan will be the primary partner to the Genesis mission. So this was announced that both sides will be round one will be investing $500 million each, so a total of $1 billion to establish collaboration between Genesis and Japanese Air Force science effort. Okay. And then that's just round one. Okay. But beginning of this was already announced at SC-HPC Asia 2026. By the way, 27 will be in Singapore. You're all welcome to come. 28 could be in Japan again, so we'll see about that. Okay, and also, but this collaboration with DOE has already resulted in a significant collaboration for this one work that won the best reproducibility award. We also won the best paper award along with Oak Ridge. So a lot of these AI for science efforts that are being done between the U.S. and Japan are really award-winning efforts. So that's really good. But it's not just about the U.S. We believe that there needs to be a global collaboration. And in fact, when people talk about sovereignty, because AI sovereignty, they only think about, we build our, like whatever language model, like a Japanese language model, that's our sovereignty. Or we build like a hardware that's sovereign. Or we build platforms and stuff like that. But in reality, it's really hard to beat this. For example, it's really hard to beat the hyperscalers. Right? It's really hard. The only people who can do this, have been able to do this are the Chinese, right, with open models. So it's really important not to be enclosed in your own domain, but it's really important for the world to collaborate. So there'll be a mutual. This may sound kind of oxymoronic, but sort of a mutually internationally dependent sovereignty will be very important. So all the nations get together, like all the list is not limited to these. And then we would be able to have a common data set, common infrastructure, common workflow, and then all the expertise get together and to develop a model on which we can build these foundational sciences. So if you go to your government and say, and they're still saying, oh, we want this, our national sovereignty model, tell them to stop, because that's not a very productive thing. The productive thing is to collaborate. Okay, about quantum, I have a few more minutes left. So we have a quantum infrastructure now fully in operation. We have IBM Kobe 156-qubit system and running. We have the Quantinuum machine, which is now being upgraded to 56 qubits. It's in operation, but it'll be 56 qubits in this August. As you see, the GPU cluster is already working. Of course, we have Fugaku. But the thing is to really build this hybrid infrastructure. Okay, that's the real focus. So that there'll be multiple quantum computers, multiple supercomputers, and the software stack to synergize all of these as a production environment. Okay, so that's the really goal of what we're trying to do, and including some of the machine that Riken is also developing. And we got some really great results, especially in collaboration with IBM. So in some sense, we are almost approaching what we can call quantum utility. And this is one of the latest papers, which got a lot of attention. So we used the entire the Heron 2 system, which is the one you saw, and then used 150,000. Actually, this is the old slide. I'm sorry. We used 150,000 nodes on Fugaku in hybrid computing to be able to determine the structure of this Fe4S, ferric sulfuric substance. And of course, the scheduling and everything is very intricate, but we were able to almost come close to DMRG in terms of performance, but with much higher accuracy. The other recent result we got, again, a collaboration between Cleveland Clinic and Riken and IBM. We were able to do a record-breaking 12,635 atom protein simulation, going like orders of magnitude beyond what the traditional quantum computers have been able to do in simulating these substances. So again, this has received a lot of attention. Well, not just building infrastructure, doing breakthrough science, along with our partners, IBM, and we'll have partnership with others, including DOE and so forth. And now finally, Fugaku NEXT, spare me a few minutes. Fugaku NEXT, so last August, we announced collaboration with NVIDIA. We picked Fujitsu NVIDIA as our development partner. Was all over the news, and we got about like 50 media attendees in the press conference and TVs and all that. So a lot of national attention. So the Fujitsu component is the Monica X processor. You see the Monica processor, the predecessor to this on the show floor. But this one will be an enhanced version of Monica. It'll be built on the 1.4 nanometer process, A14. It'll have three enhancements compared to Monica. It will, A, have a pretty good AI performance on its own. Right? So it's not, so of course GPU will be superior, but as a CPU, it'll have fairly good AI performance. Much faster memory bandwidth, much faster compute for low precision compute. It will also have be able to attach directly to an NVIDIA GPU, so it have NVLink Fusion embedded, and it'll be of course very highly scalable, etc. And so very highly power efficient. It have 192 cores, so etc. So it'll be. We hope this will be the CPU of choice in data centers, not just for Fugaku NEXT, but as a standalone, being coupled to NVIDIA GPUs. We hope that this will penetrate the hyperscaler market. So Fujitsu will be able to sell these in the hundreds of thousands to millions. So that's our goal. GPU, of course, we're working with NVIDIA very hard. The machine you just saw was actually also a development platform. It has a day job as an AI and a quantum simulator AI and also AI machine, but also we're using this as a development machine for Fugaku NEXT, especially the applications and software. And we call it phase N-2. Then the phase N-1, we hope to have a Monica Rubin machine in the 27 or so time frame or something of sort. I can't really tell you what the size of this will be. Then in 29, we'll have the Monica X, some Feynman variation. Will be the Fugaku NEXT machine. Okay. So we have this phase development, and the goal is really tough because we know that we can achieve some factors of the speed up, but compared to the speed up from the K computer to Fugaku, when we got hardware, there was a 40x performance boost. And the software, so maybe like 3x. So in total, there was 100x speed up. But this time, in terms of hardware, we anticipate we can get maybe like 6x or at best 10x. So in order to achieve 100x again from Fugaku to Fugaku NEXT, really the software has to be there. It really there needs to be acceleration in terms of the algorithms, software, etc. So we're working in various fronts to really innovate in the software and algorithms to achieve this 10x speed up, exploiting the properties of hardware. If you saw my recent paper, FP8 is all you need, and that's one of the efforts that's ongoing. Okay, so hopefully we'll achieve like 100x maximum, or even 1000x if we have appropriate use of surrogates. And in terms of AI performance, we hope to get approach or even to approach Zettascale in some precision. So it's probably will be one of the Zettascale machines in low precision in 29. Okay, and but software, algorithm, everything is very important, so that's what we're working on. I'm running out of time. So we're trying to get, unlike China, who can develop the machine entirely on its own, right? Although not the latest, but still, I have high respect for Yutong and her group. Japan's strategy is to work together with other partners. So we have our own technology, like Monica. We have other photonics, and we have various memory technologies, et cetera, but we can't build it just by ourselves. So to partner with other entities like the US and other places, and combined, we'll be able to design this state-of-the-art latest and greatest systems, and that's a made with Japan strategy. So we're playing this game because we can't do it alone, but on the other hand, we'll be one of the key players in this global ecosystem. That's the game. That's sort of the strategy we're playing. Okay? So with that, I'd like to end, and thank you very much.
Thank you, Satoshi. Always an inspiring talk.